All right, let me improvise an intro. Welcome to Rustacean Station, live at Rustfest. Well, I mean, it's live for me, not for anyone listening to this. We are here with some micro interviews to just, I guess, capitalize on the fact that we are surrounded by people who are themselves embroiled in Rust every day, kind of just in the soup. And our first ingredient in the Rust soup is Ollie OBK. I don't know your actual name.
Well, Ollie comes from Oliver.
Okay.
OBK is just my hometown.
Okay.
Short.
Cool. So who are you?
Right now, I am working on improving privacy and big data analyses, making sure that cryptographically that we can't do anything with your private data. Other than that, I have been doing my PhD for the last few years, and doing which I have been doing most of my Rust compiler work. And right now I'm also working on the Rust compiler, mostly on const-eval.
Const-eval. And I think today I wanted to ask specifically about a component called Miri, which I have heard a lot about. I think let's start from the beginning, because not everyone, I'd say actually very few people, kind of understand the whole structure of the compiler and like where Mir fits in and where const-evaluation fits in. And so let's just go real quick. What is const-evaluation?
So const-evaluation is the process of computing some kind of math or other operation at compile time, most notably for computing the length of arrays, or for computing the discriminant of an enum variant. So if you have a C-like enum, all the discriminants can have integer values, but it can also have values computed from more complex expressions.
Okay. And what would you do with const-evaluation?
So I mostly do like whatever is kind of fun and a little bit cursed. But the main use case is actually to prove things at compile time instead of at runtime. So you move some information to compile time. For example, instead of using a vector, you use arrays, because then you know the length at compile time. And if your use case would be always vectors of the same length that you would know at compile time, you could use arrays. And the more powerful const-eval gets, the more things you can do with it.
Mm-hmm. So kind of just moving operations from runtime to compile time, kind of running parts of your program up front when you, the developer, compile it, and then like shipping that off to your users, and then they get the benefit of all that work that's already done for them.
That is one part. You save runtime operations, but the other thing that is mainly why I got into it is you can prove things at compile time by simply not having errors. Because if you otherwise had some kind of runtime error, that would happen once the user runs it. But if you do move things to compile time, you get errors at compile time. And
that sounds great. We love more compile time errors around here. If you're listening to this podcast, I'm sure that you're the same way. And we'll talk more about proving things later, but I want to talk, before we get into that, the whole nitty-gritty, what is the history of Miri? And so I think for me, it's pretty old-ish project, kind of like began, I think Scott Olson or something was the person who they were working on it as part of an academic project for maybe their PhD or something. And do you know more than that?
Correct. It was their master's thesis. And the project was actually started right around when MIR was introduced to the compiler.
So around 2012, 2013? Or sorry, no, 2016, 2017. My time's messed up.
Yeah, so when MIR was introduced, we still had an old const-evaluator, which is essentially just like something working on the syntax tree of the language and like does so-called constant folding. So it folds syntax components together. So if it sees like 2 + 2, it like knows, okay, there's an integer, and there's a plus. I can figure out that this is 4. And simple. It is very simple, and is also very limited, because once you get into like loops and local variables, it gets like, how do you even do that? Like we never implemented it because it's very hard. And so with the advent of MIR, there was a new opportunity for the tool now known as Miri, which is Mir Interpreter. So MIRI, the I stands for interpreter, meaning we are interpreting the MIR sort of like a virtual machine runs bytecode, but our bytecode is MIR. And MIR is different from the usual syntax structures that like display how your source code looks. because there is no connection to the syntactical version anymore. It is basically how later compiler stages like optimizers and so on process this data. So you don't have things like loops anymore. It's basically just all full of go-tos and ifs, and that's it.
Mm-hmm. Yeah, so MIR, I guess, kind of even for people who aren't even like at all familiar with Rust compiler, it's just a language used internally in the compiler, and your Rust code gets compiled to this, and then the Rust compiler does various analyses on this, and at some point converts that into LLVM IR, which is what LLVM wants to work on. Okay, and then so we have an interpreter in our compiler, is what you're saying.
Right. So before we had an interpreter in our compiler, we had the Miri project, which was an external project to the Rust project. And what it did is it connected to the compiler API and used the MIR data structures to then implement an interpreter on top of that. And the next step after that was taking parts of the Miri project and putting them actually into the compiler. So there's a core component of this virtual machine, this Miri interpreter, which we want for the const-evaluator. We don't want everything. For example, the full Miri tool had support for doing FFI calls and that. And const-eval doing FFI calls would be something very odd, and we don't want this. So we split out a core component and moved this into the compiler. And then the compiler is using this core Mir engine, Mir interpretation engine, for the const evaluation. And at the same time, Miri is using this engine. Since it's already using the compiler API, it just uses now the engine from the compiler API instead of its own. So there's a big shared piece of code between the Miri tool and the const evaluator. This is called the Miri engine.
Okay, and then so not all of Miri is actually in the compiler.
No.
Are there plans to eventually kind of move the entire thing, or are we trying to move to a status where less things live in the rustc repository directly and we kind of link against? Is it going to be a crate on crates.io, or is it going to be kind of a sub-module private kind of thing living in the Rust repository organization?
So Miri right now lives as a submodule inside the Rust project, but mostly so CI notifies us if the compiler changes in ways that break Miri. Miri is not actually like a core component of the Rust project. It is, although, installable via RustUp, so you don't actually need to compile it yourself.
I want to talk about that later because you've told me some cool things that we can do with that.
Yeah.
But for now, just to finish up the history, how long have you been working on the compiler in Miri?
Okay, so in Miri, I've only been working on for like 2.5 years, I think. Before that, I was working on the old const-evaluator. And once Miri started taking off, I moved completely over there and never touched the old const-evaluator again. For a short time, we actually had we had 3 const-evaluators in the compiler. So I was talking about how we have the new one, the Miri based one, but we also had the old const folding const evaluator, but there was also an LLVM based const evaluator, which was used for statics. And this was a very odd situation to be in, to have these 3 const evaluators that all had different feature sets. So they were non-overlapping in some places. They were so everything had some features that the other parts didn't, except for the Miri one, which had definitely all features that the other 2 had. So at some point, once both of them were running in parallel, we were checking them against each other to make sure that the new Miri const evaluator did not change behavior. So we were basically running both and checking the result. And once we were sure everything is good, we removed both of the old ones.
So it has parallels to kind of the new borrow checker, where we kept the old one around for a long time, kind of comparing with the new one. And once we were pretty sure that everything was working out well, you remove the old one.
Right.
Oh, this one seemed more transparent. There wasn't as much ceremony because I haven't heard about this. What time frame was this happening in?
I started in October with like a huge pull request to add the...
You mean last month, October?
No. So, sorry, this was October 2017, I guess?
Okay.
Yeah. And once that was merged, I started immediately working on actually using the new const-evaluator everywhere, which took another 3 months, which was in March. And I managed to get it merged after a few hundred commits of fixing it up. just after a release. So we had another 12 weeks before it came into stable. And that was very good because in the next few weeks, we were encountering all kinds of problems with it. They were all small problems, but like some people had some odd crates that did curious things, and we had to adjust for that to work again.
Okay, that sounds great. And certainly now we appreciate having more const evaluation things. I know that, for example, the first thing that came to stable Rust was the ability to write struct constructors. I think previously, or maybe no, it was being able to call functions, associated functions. And so, whereas previously, if you wanted to write a thing in a static context, you had to just call the struct constructor. And if you had a private field of that struct, you were out of luck. And so normally in Rust, you would write like string : new or vec : new, but you couldn't call a : new thing in a static. And so we were just kind of, and the original impetus for this was to allow that to happen, which I'm not sure if that was pre-Miri or post-Miri, but certainly we have more things available these days.
So that was actually pre-Miri for some types and for some kind of arguments. So you couldn't do like destructuring, you couldn't have local variables, some types just like you couldn't really work with references and so on. And with Miri, like all of these limitations, they just went away because like structurally they don't exist. We actually had to re-implement some additional checks to not allow too much because Miri was so powerful.
Not allow too much? Why wouldn't you want to allow more things?
Well, we want to allow these things, and we slowly started removing these checks again. But we wanted to take it slow. So there's some things where we weren't sure like how they should be exactly designed. For example, right now you cannot take mutable references inside constants and const functions, even if it would technically be sound, as if you look at it as a human. It's just like we want to make a nice analysis that permits you to do everything that is okay, but not the things that are not okay. And this is work in progress.
So then, in terms of today, what can we do with Miri? What's like the newest? Like, so what is the newest stable stuff? I think I've seen some things where like addition works now on integers, for example. So you could have like const to right. That's always worked possibly. That's just constant folding. But like, what's the newer? I think maybe last December I saw some of the like newest stuff.
Again, separating Miri, the tool, and the const-evaluator. The const-evaluator, like very recently, like 2 days ago, you're able to take the length of a string or of an array at compile time. Mm-hmm. And this by itself was already interesting to a lot of people because they could include bytes with the macro, a file, and then get the length of the file at compile time.
Oh. Very interesting.
And
yeah.
Someone else was also experimenting with this and implemented string concatenation at compile time.
On static strings.
On static strings. It is very, very, very unstable and very, very much undefined behavior, but you're doing it at compile time, so it's not as bad.
Well, let's actually segue into that. Undefined behavior at compile time. Yesterday at lunch or at dinner, you were talking to me very excitedly about various things involving undefined behavior in Rust and Miri's use for detecting undefined behavior. Now, I think in this case, was it Scott Olson who part of his original thesis was the idea behind Miri originally was to try and like detect undefined behavior, or am I just inventing that?
I believe at the beginning that was not the intention. I believe in the beginning it was mainly used to be used as a new const-evaluator, but here comes along Ralph Jung, who then had a big vision of making sure we can prove that a program has undefined behavior by running it in Miri, the tool. So this is independent of the const-evaluator. Const-evaluator does not do a lot of undefined behavior detection. But Miri, the tool, if you run this on a program, it will try to detect as much undefined behavior as it can. It is very hard to actually do some kind of undefined behavior that it cannot detect yet.
I want to kind of back up here too, because it's kind of blowing my mind in some cases. Let's just talk about undefined behavior as a general concept, like in C. So in C, part of the thing with undefined behavior is, hey, here's a thing that we as a compiler, as a language, you can't do legally. It is illegal to do these things, but we can't ever tell if you do. At least, not tractably or all the time. And so in C, there are things that you just shouldn't do, because if you do, you are writing undefined C, which is not like compliant C, which happens all the time. It's just unavoidable. It's very easy to do. In Rust, it should be harder to do, but if you have an unsafe block, you can still do undefined things. But I think you were telling me that your goal is to eventually make it so that Miri can detect 100% of undefined behavior in Rust. So what does that even mean? Is it even undefined anymore if we can detect it 100% of the time?
So we need to remember that Miri runs your program like it were a virtual machine. So it will only detect if this specific run had undefined behavior.
I see.
It is not a general, your program is free of undefined behavior if Miri passes. It is, in this run, Miri did not find any undefined behavior, and except for the 2 or 3 edge cases that we know of, every kind of undefined behavior would have been detected.
And those edge cases you're saying you're working on making those go away.
Right. And but still, only for the specific input you gave to this specific program run, you would have had detected undefined behavior. If you change the input, you would have to rerun again to check if that input would cause undefined behavior.
Interesting. So it's more like the sanitizers kind of the LLVM provides, but tailored for Rust specifically, and I guess hopefully more complete. You wouldn't need like both an address sanitizer and a thread sanitizer, because it should just cover all undefined behavior for any given run. Is it much slower, this virtual machine, than you're laughing? That's
Yeah.
a good sign, right?
No, so it is ridiculously slower. It is several orders of magnitude slower.
Okay.
The idea is not to run like very large programs in it, but like to run for example, your entire test suite in it or something.
Okay.
But only the unit tests, like only small self-contained things. And mostly around your unsafe code, you will at least cover the unsafe code, because the safe code should be fine. So yeah, so you should be running your tests inside Miri, especially if the source code that is employed has unsafe code.
Mm-hmm. And how you would do that is you would use this rustup component, which you mentioned before. If rustup install Miri, and then what?
Rustup component add Miri.
Rustup component add Miri.
Yeah, and then you have a subcommand available, which is called cargo Miri. And cargo Miri takes care of everything for you for running this virtual machine. What you then can do, if you have a binary, you can do cargo Miri run, and it will run your program as if you ran cargo run. So you can actually pass arguments, and since it can open files and read files and write files, it will do a lot of processing that you could normally do.
And could you compose that with cargo tests somehow to automatically use Miri on your entire test suite?
So exactly, we had cargo Miri run, which runs a binary, and we have cargo Miri test, which just runs your entire test suite.
Ah, okay. Nice. Very cool. And so that sounds fantastic. Would you recommend people do that today? Is it in a place where you think it would work for plenty of programs?
So it works for plenty of programs, especially those that do not have networking, that do not have threading, and so on. So if it's very simple tests, that works. If you have just some tests that won't work, you can CFG them out, because there's a CFG Miri flag that you can use. And then you can just comment out, or not comment out, but CFG out those tests that don't work. And that way you can run your entire test suite through Miri. As we already mentioned, it can be quite slow. That is one part. And there is lots of things that Miri simply can't do. If you're calling an arbitrary C function, we don't know that C function. Our virtual machine doesn't know that C function. Mm-hmm. Most libc functions, we know them. So we implemented them to actually work. But if you have some custom C functions that just doesn't work, you can still try to run this by implementing the C function as a shim in your own Rust code.
Cool. And then, getting back to constant evaluation stuff, does it let us do anything special with the unsafe keyword in constant contexts?
So at the MIR level, we don't see unsafe anymore. Mm-hmm. It's just not there anymore. So you can just run this technically. We have some static checks that prevent you from actually doing things that we don't like you to do. Mm-hmm. Not because we want to forbid you from doing this, because some of these things can actually break the type safety of the Rust compiler if you do undefined behavior at compile time. And they do this in very subtle ways. So there's more undefined behavior at compile time than at runtime. One example would be you cannot compare pointer addresses at compile time, even though that's trivial at runtime.
Because you have no address. There's no memory
Right.
space. Or I guess there is, but it's not the user's memory space.
Exactly. So that we could compare it and give you some random result. Even if that were okay, the problem is if you do the same comparison at runtime, you get a different result. And now you have something where the compile time gives you a different result than the runtime. And this can actually be used to like break array indexing checks and so on. So this is not something we want to do.
Okay. And then in terms of upcoming, I know you said that Miri is further along than const-evaluation is. So const-evaluation is kind of catching up with features where you gradually feature flag them and add them. I think you mentioned that loops are coming soon to constant evaluation through Miri, also branches, so if, that kind of thing. Is there anything else?
Right. So these two are like the big ones that unblock a lot of things. And there is almost all of the stumbling stones have been taken away now. We basically just need to implement the analysis that allows you to feature flag the things again. After we have those, there's an active RFC for allowing you to call trait methods at compile time. And this will allow you to do various curious things. For example, we can get a part of the way there to running 30 at compile time.
30? Oh, okay, 30. Okay, yeah. Interesting.
Which would allow you to, for example, parse TOML files or JSON files at compile time into a data structure, into a static. So your config files that you normally do like with a lazy static or something, you could do that at compile time.
Whoa.
Which is especially interesting to embedded developers because they can now use configuration files that were previously not, they previously couldn't use.
So cool. And then let's also give shout outs to everyone else who works on Miri. So you want to give any names, people who help you out, or who to ask for help if they had more questions to say?
Ralph Jung and I, who are merging pull requests, and Ralph is keeping it up to date, so it's always working with the latest compiler. Christian Poveda is implementing loads of new features into Miri. For example, he implemented file reading and writing, which is a very cool feature. And on the compiler side, Santiago Pastorino and Wesley Weiser are implementing loads of new MIR and MIR optimization features, which often depend on const-evaluation. So, for example, constant propagation. So optimizing runtime code. We do this by just running the const evaluator on normal runtime functions and like letting it go as far as it can.
In terms of like getting more people to help you work on Miri, have you been like onboarding people or doing kind of like sponsorship of people who want to tackle easy issues or learn more about this kind of stuff?
So I'm mentoring a lot of issues about both in the compiler and in Miri. If there's any interest, I'll happily take on more mentees. Right now I have like 3 or 4, but there's definitely space, time available to do a little bit more.
Great. I know plenty of people are looking forward to a lot of new const stuff coming in the future. Now that we have async await, we got to have new things to look forward to. So, okay. Thanks a lot for talking to us. It was great hearing about this. Hopefully you get some more interest in this. Otherwise, people will just happen to know more about it, which is always good. All right. Thanks for coming.
Thanks.